4 nanometers. That's the number TSMC's own engineers said was basically impossible without their most advanced machines. China just did it anyway. And they didn't do it by breaking the rules of physics. They did it by breaking the rules of the game itself. Here's the number that's making engineers at TSMC uncomfortable right now. A Chinese chipmaker just claimed they can hit transistor density equal to a 1.4 nanometer chip. That's not a small chip. That's one of the most advanced processors on the planet, the kind that powers flagship phones and cutting-edge AI systems. And they claim they can do it without the one machine every other company on Earth needs to make chips that small. No access to the most advanced lithography tools. No permission to buy the equipment that Taiwan, South Korea, and the US rely on. And yet, here's the number anyway. Before we go further, you need to understand something. This isn't really a story about a smaller transistor. It just looks like one on the surface. What's actually happening here is different, and once you see it, the whole story changes. Instead of trying to shrink the transistor itself, this company is trying to shrink something else entirely. Time. The time it takes information to move from one part of a chip to another. That sounds like a small detail. It's not. It might be the biggest shift in how chips get built in the last 20 years. To understand why that matters, you have to go back to the simple formula that ran the entire chip industry for over 60 years. Make the transistors smaller, fit more of them into the same space, get more computing power without raising the price too much. That's it. That's the whole game plan behind Moore's Law. The idea that computing power roughly doubles every couple of years. For decades, this formula just worked. Every new generation of chips was smaller, faster, and cheaper than the last. It felt like it would go on forever. It's not going on forever. That formula is running out of road, and the numbers prove it. Take TSMC's next generation chip technology, the one built to replace their current top-of-the-line process. Engineers were expecting a big leap forward, like the leaps of years past. Instead, reports point to something closer to a 6% gain in how many transistors fit into the same space. 6%. A decade ago, jumps like that were considered a disappointing year. Now 6% might be considered a win. That tells you everything about where this industry actually stands right now. The easy gains are gone. Now put yourself in the position of a Chinese chipmaker trying to compete in this environment. You're not just dealing with a slowing industry. You're dealing with an industry that's slowing down while also being locked out of the most important tool in the entire process. The most advanced machines used to print these tiny transistor patterns come from one company, and Chinese chipmakers are barred from buying them. So while the rest of the world debates how to squeeze out the next 6%, Chinese engineers are stuck working with older tools that were never designed to build anything this small in the first place. Their answer to that problem is not new equipment. It's a technique called multi-patterning. Instead of printing an extremely fine, extremely small pattern in a single pass, the way the most advanced machines can, older tools split that same pattern into several separate steps. Print part of it, etch it, print the next part, etch that too, layer by layer, using machines that were never built for this level of detail. It works. Chinese chipmakers have already used a version of this method to reach what many consider a 7 nanometer equivalent process, a result that surprised a lot of people who assumed it wasn't possible without the newest tools. But here's the honest part of this story. This method is not free. Every extra pass through the machine adds cost. Every extra step adds more chances for something to go wrong. This isn't a shortcut. It's brute force engineering, squeezing every last bit of performance out of tools that were supposed to have hit their limit years ago. And eventually, no matter how creative the workaround, that approach runs into a wall. You can only push old machines so far before the physics simply won't cooperate anymore. So the real question isn't whether Chinese engineers are clever enough to keep pushing multi-patterning further. They clearly are. The real question is what happens once that road runs out completely. And that's exactly the point where this story stops being about smaller transistors and starts being about something nobody expected. What if the entire industry has been trying to solve the wrong problem this whole time? Picture your phone in your pocket right now. It feels warm sometimes, right? Especially after a long call or a heavy game. You probably assume that heat comes from the chip doing hard math, crunching numbers, running the app, powering the screen. That's not actually where most of that heat comes from. And once you hear the real reason, you'll never think about computer chips the same way again. Most of the energy inside a modern chip isn't spent thinking. It's spent traveling. According to Huawei's own engineering team, more than 80% of the energy used inside a data center chip goes toward moving data from one place to another, not toward actually processing it. Read that again. 80%. That means the giant, expensive, cutting-edge processors running inside AI data centers right now are spending most of their power just shuffling information back and forth, not doing the actual work you'd assume they're built for. That one fact changes everything about how you should think about chip performance. For years, the entire industry obsessed over one thing: make the transistors smaller. Everyone assumed that was the main lever for better performance. But if 80% of the energy is being lost to movement, not computation, then the transistor was never the real problem. The wiring was. Here's a simple way to picture it. Imagine a chip as a giant packed city. Instead of buildings, you've got billions of transistors. Instead of streets, you've got tiny metal wires connecting them stacked more than 20 layers deep. Every time one part of the chip needs to talk to another part, a signal has to travel down these tiny highways. And just like real traffic, that trip costs something. The wires have resistance, which slows the signal down. They also act like tiny batteries that have to charge and discharge every single time information moves through them. The longer the trip, the more energy gets wasted and the more time gets lost. Multiply that by billions of trips happening every second, and you start to see why so much power disappears before any real computing even happens. This is also the real reason your phone and laptop stopped getting dramatically faster every year the way they used to. For a long time, engineers could just crank up the clock speed and get more performance. That stopped working years ago, and this wiring problem is a big part of why. You can't keep speeding up a highway system that's already jammed with traffic. So here's the part that flips the whole story. If the real bottleneck is distance, not transistor size, then the fix isn't to keep shrinking the parts. The fix is to shrink the distance between them. And there's one very simple way to do that. Stop laying everything out flat, side by side, the way chips have been built for the last 60 years. Start building up instead. Think about folding a flat sheet of paper in half. Two corners that used to sit far apart from each other are now sitting right on top of one another. That's the exact idea behind this new approach. Instead of spreading the chip's logic out across a flat surface, sections that would normally sit inches apart get stacked directly on top of each other. A trip that used to take a signal across several millimeters of chip space can now take place across a few microns of vertical distance instead. That's not a small improvement. That's a completely different category of speed. This is the real idea sitting underneath the tau scaling name you may have seen mentioned in recent announcements. It's not about cramming in a smaller transistor. It's about attacking the timing delay directly, cutting down how long it takes information to move through the system in the first place. Once you understand that, the entire strategy stops sounding like a marketing buzzword and starts sounding like a genuinely different way of building a computer chip. But before anyone starts celebrating this as a clean solution, there's something important you need to know. Stacking logic on top of logic doesn't just solve the distance problem, it creates a brand new one. This next problem might be even harder to fix than the one it was designed to solve. Here's a strange fact about engineering. Sometimes the smartest solution to a problem is also the fastest way to create a brand new one. That's exactly what's happening here. Stacking chip logic on top of itself solves the distance problem beautifully. But it opens a door to two new problems, and one of them might be hard enough to break the entire plan. Let's start with the first one. Once you stack two layers of logic directly on top of each other, they need a way to actually talk to each other. And they need to do it constantly, potentially billions of times every single second. If that connection is slow, you haven't solved anything, you've just moved the traffic jam somewhere else. So the entire idea only works if engineers can build an enormous number of extremely fast, extremely tight connections between those stacked layers. And that brings us to the one number that this entire announcement actually rides on. That number is 1.5 microns. That's the target spacing for what's called hybrid bonding, the tiny copper connections that link one layer of a chip to the layer sitting right on top of it. On its own, that number might not mean much to you. So here's the comparison that should make your jaw drop a little. Today's best chip makers, including AMD, Intel, and TSMC, are working with bonding connections closer to 9 microns apart. 9 microns is considered advanced. 1.5 microns isn't a small step forward from that. It's roughly 6 times tighter than what the best labs in the world are currently doing in mass production. That's not a modest claim. That's one of the most aggressive manufacturing targets announced in years. And every time you push connections that much closer together, you're not just tweaking an existing process. You need new tools, new materials, new methods for testing whether millions of these tiny connections actually work correctly. This is the kind of number that either becomes a defining breakthrough or becomes the reason the entire timeline slips by years. Right now, it's genuinely too early to know which one it'll be. But even if engineers manage to hit that number, there's a second problem waiting right behind it, and this one is arguably worse. It's heat. Think about it this way. Stacking memory chips on top of a processor is something the industry already does today, and it works fine because memory chips don't generate much heat. They mostly sit there and store information. Logic is completely different. Logic switches billions of times every second, and every one of those switches generates heat. Now take two active, heat-generating logic layers and press them directly on top of each other. So you've just packed twice the heat into the same physical space with far less room for that heat to escape. In a data center, this is a manageable problem. You can throw enormous cooling systems at it, liquid cooling loops, massive heat sinks, entire rooms built around temperature control. But here's the detail that raises the stakes on this entire story. The first product this technology is aimed at isn't a data center chip, it's a smartphone processor. A phone doesn't have room for a cooling system, it's thin, it sits in your hand, and it already struggles to stay cool during something as simple as a video call. Stack 2 logic layers inside that same tiny space, and the heat problem stops being a technical detail. It becomes the single biggest question mark hanging over the entire plan. Anyone who has spent real time working in chip design will tell you the same thing. Getting a new manufacturing process to work in a lab is one kind of challenge. Getting it to survive inside a mass-produced device that people carry in their pocket all day is a completely different level of difficulty. If the heat problem gets solved, this becomes one of the most important shifts in chip design in years. If it doesn't, the entire roadmap risks becoming a lab success story that never makes it into your hands. And that's exactly the tension worth watching as this story moves forward from here. Here's a question worth asking before you get too impressed or too skeptical. Is any of this actually new, or is it just an old idea finally pushed to its limit? The honest answer might surprise you, and it changes how you should judge everything you just heard. Stacking chips on top of each other isn't some brand new invention. The industry has been inching toward this for years. AMD already stacks extra cache memory directly on top of its processors. High bandwidth memory chips, the kind used in AI accelerators, already stack up to 12 layers on top of one another. Research labs around the world are already working on stacking transistors themselves, not just entire chips, through a technology known as CFETs. So when you step back and look at the bigger picture, this isn't some radical leap out of nowhere. It's the same direction the whole industry has already been walking in. What's different here isn't the idea, it's how far someone is willing to push it, and how fast. That context matters because it leads directly to the part of this story that deserves the most scrutiny. The headline number everyone is repeating is that this new approach could eventually match 1.4 nanometer class transistor density, the kind of density normally associated with the most advanced chips on the planet. That sounds like proof that older manufacturing tools have somehow been made equal to the newest ones. That's not quite what's actually happening, and the difference matters. What's really been demonstrated is a jump in transistor density of around 55% compared to a flat, non-stack design, achieved by folding 2 layers of logic on top of each other. That's a real, genuinely impressive result. But stacking 2 mature manufacturing processes on top of one another doesn't create a brand new, smaller manufacturing process. It doesn't shrink the actual transistor. It just lets you pack more of an existing transistor into a smaller footprint by building upward instead of outward. So when you see the phrase 1.4 nanometer equivalent, the word equivalent is doing a lot of quiet work in that sentence. It's a meaningful achievement. It is not the same thing as inventing a true next-generation node. That distinction is exactly what separates this new approach from the old formula that ran the chip industry for 60 years. Moore's law was about getting more transistors for less money, generation after generation, almost automatically. This new approach doesn't work that way. It buys you more raw performance through clever packaging, tighter connections, and smarter engineering. But it comes at a real cost, more complex manufacturing, more expensive tools, and a thermal challenge that still hasn't been fully solved. In plain terms, this trades cost efficiency for pure performance. That's a legitimate strategy. It's just a completely different bet than the one the rest of the industry has been making for decades. So where does that leave things? The bonding technology needed to connect these stacked layers still has to be proven at a scale nobody has hit before. The heat problem inside a smartphone-sized device still has to be solved, not just theorized about. And the gap between a lab demonstration and a phone sitting in millions of pockets is still enormous. None of that means this fails. It means the next year or two will tell you far more than this announcement alone ever could. Here's the real question worth sitting with. If the constraint on advanced chips was never really about buying better machines, and it was actually about smarter engineering the whole time, how much of the current lead held by the biggest chip companies is really safe? That's not a question with an easy answer right now, and it's exactly why this particular story is worth following closely, because the next update on this technology might tell us a lot more than this first announcement ever could.